Yes, it's recording. Yes, please let me know if my screen is visible.
I can see yours.
Yes, thank you. Yeah. Good evening and a warm welcome to one and all present in the webinar. IEEE Bangalore section, IEEE Site Bangalore section, and IEEE Women in Engineering Affinity Group Bangalore would like to invite you all for the talk AI for Storage and Storage for AI by Ms. Kalapriya Kannan. It is our distinct honor to introduce today's distinguished speaker, Kalapriya. She currently holds the prestigious role of Master Technologist at Hewlett Packard Enterprise HPE, where her expertise serves as the architectural foundation for the analytics and insights stored within the HPE GreenLake Data Services Cloud Console. In her role, Calabria stands at the forefront of innovation, pioneering cutting edge solutions in the realms of analytics and insights. Her work transcends the complexities of diverse data formats, substantial data volumes, and the worlds of data visualization, analytics, and reporting. But her influence extends far beyond product development. Calabria's thought leadership shapes the very roadmap of her industry. Before joining HPE, she embarked on a remarkable journey at IBM Research as a senior research member, leaving a mark on the world of technology and innovation. Calabria's commitment to innovation shines through her extraordinary portfolio, boasting 65 granted patents, with several others poised for acceptance and publication. Furthermore, she is a prolific author with nearly 75 papers presented at various international conferences, solidifying her position as the thought leader in her field. Yet, Calapria's contributions span beyond research and development. She has played pivotal role as a chair, organizer and program committee member at numerous international conferences. Most notably, she was appointed as a chair for the HIPC 2022 workshop on data fabric for hybrid clouds and assumed the role of chair for the IKDD COTS Comad tutorial track in 2022 and 2023, exemplifying her leadership in driving discussions on cutting edge topics. Her influence extends into academia, where she played an instrumental role in forging robust connections between universities and industry. Her leadership, both at IBM Research and HPE Storage University Relations, underscores her commitment to nurturing partnerships with esteemed universities in worldwide. In her free time, Calapria's passion for giving back to the academic community shines through. She selflessly shares her wealth of knowledge and expertise by delivering lectures and teaching courses at several prestigious institutions in India, including her alma mater, BITS Pilani. Calapria also serves as adjunct faculty at BITS Pilani and holds a vital position on the Board of Studies for the RVCE Bangalore and SREC Coimbatore. Our today's speaker will be sharing insights from an industry point of view about the following topics: the role of AI for storage and storage for AI applications for a sustainable future, building metadata when data at rest, accelerating AI applications with storage features for sustainable outcomes, problem statements that matter to the industry and need of the hour to be solved by technologists, researchers, academicians, and students. Before we hand over the session to our today's speaker, we would like the audience to share their questions in the chat. Post the talk by the speaker, we will open the session for Q&A. Now, we welcome Ms. Kalapriya Kannan to walk us through the webinar. Over to you, ma'am.
Kalap, we can see your screen, but I think we can't hear you.
I think I was on mute.
Yeah, we can hear you now. Thanks.
Yeah. Okay. Okay, so I would not do anything more of my introduction. I think it was a well-written introduction for myself. So I'll just start with laying down what is there in for today. And before that, I would like to thank all those who have taken the time to attend it. I hope you will get something out of this thing, both from what's happening in the industry as well as what is some of the research roadmaps that probably is available in this space, right? So with that, I'm going to start laying down what the agenda I have for today. Since I just assume that made an assumption that the audience over here are going to be from diverse backgrounds, starting from students to all the way from academic sector as well as from this thing. So the topics I picked up are a mix of a couple of things, starting from first explaining where is the interaction of the AI with the storage with the very simple examples. Then I would also go into some of the things that that has been happening in the industry as well as what we have done as part of a couple of work in actually helping storage address some of the AI critical stuff. The other thing is also that it's just not storage helping the AI. The AI is also helping the storage backwards in terms of one to the customers as well as there is going to be the storage helping AI helping the storage itself in terms of management internally. So that is something which we would look at the later part of it. And then I'll close it with some of the topics that is open for research, because that is something which I don't think we can answer today, but hopefully that if somebody is interested in doing their PhD or doing their masters, these topics should help them actually take up a few things from here and then delve detail into those topics. Okay. Apart from that, if there's anything else that you think that I can address while we are doing the talk, you could always certainly post the questions in the Q&A and I'll be glad to answer those. Okay. So with that, I'm going to start my presentation. And before I get into it, there's a host of people I would like to thank because some of the work that I'll be presenting today in the later part, which talks about how storage can enhance the AI's workflows and pipelines in terms of both speeding up and also having some a different experience with that. We have been doing quite a bit of work in the past 2 to 3 years, I would say, and we have actually got some interesting results from this, which I'll be sharing today. So I would like to thank all the members of our team, first starting with Suparna to Bruce to Chaitra, who's currently not with HP, but she has been with had been with us for a couple of years in this work, Krishna and Chirag and Sagar. And all the kind of internet material that I have done, there's been a plethora of material that I have borrowed from the internet to make the case. So I would like to thank all those content which was made available to us free for us to use in this thing. Okay, so with that acknowledgement, I will start with a few icebreakers, and maybe for these icebreakers, since it's going to be question and answer, and I would like you to answer those, and probably I'll pick up some answers from there and see whether it's going to be matching some of the things. Okay, so see, the session is primarily, although it's kind of mix, I would also encourage all of you to ask questions. If I see a question which is required to be answered immediately, I would take the time to do that. So please feel free to post your questions, and no question is a wrong question, right? So at least you should be putting the questions out, and then let's see how the answers would go. Okay, so let me start with certain icebreakers. I certainly need to find out where the chat box is, but let's start with the first question, right? Because I wanted to drive down where the bottleneck is. So the first thing that I would like to look at is what is the current data size looking for? So in industry general, I would like to ask, but probably we can take one specific thing, say of Facebook. If somebody can quickly put it out, what's the number that you are looking at and what's the size category, that would be something which we can look at. So if you can just quickly post a few numbers, probably we can look at it from the answers and then we can build on, because my next question would be something building on top of this. So yeah, I just need to understand how these chat would be. So yeah, if you could just post your answers on your chat box to everyone. This is a nice number to start with. Any more answers? Okay, 6 petabytes. Okay, so we are close to it. I mean, it roughly ranges from 3 to 4 petabytes. This is officially published number from the Facebook. Probably there are, it's growing every day, so it's not a point in time. So you're close to it. I mean, whoever has answered it's Raju. So it's 6 petabytes. So it's roughly like 3 to 4 petabytes is a starting time or a starting thing, right? Okay, so the next question that I would like to start putting it up is, what is the size of the data on which the GPT-3 was trained? Is there any number that you would like to put over here? Any wild guesses are also fine, you know. I mean, probably you can use the chat GPT to do that itself, to ask how much it was used to train. Okay, 10 seems to be good starting number. Okay, 50. Okay, I see an answer which is closer to the thing. It's roughly in the range of like 45 to 50 terabytes of data it was trained. Now the question that is the next one is the most critical thing, because we wanted to understand what is that it is related to the storage, right? Now here is where the question is, and probably you could take it offline and do this math. So supposing you are able to read an IO size, just for an example, right? There is a 64 KB reads that you can do per call. Now, how many IO calls are required for reading the data size of a GPT-3 training data, right? So which is essentially the question I'm trying to drive over here is, it's fancy and fantastic when you look at the numbers that is there out, how much of data is available and how much of data is used for training. But the question to answer is, how is it related to storage, right? So the question is really in the crux of answering, what is the kind of number of IO calls we are looking at, and what is the overhead in doing these IO calls to this thing, okay? So I'm not going to take this thing because I have also given you one nice example over here in the side. It's not an example, it's basically putting out how much of data is available over here. So it's 47 terabytes. You know, you can work out the math of, if it is 64 kilobytes, you know how many calls it's going to be, right? Now that is where the whole issue starts, right? I mean, there is this whole component of storage. Storage has the data, and storage is primarily the interaction to it with the computer is through the IO calls. And that is where we are going to look at how the storage is going to be for the AI applications itself. So when I say storage for AI, there are two aspects of it, right? So one is today, what is storage trying to do in order to help AI? Maybe, you know, in terms of throughputs, in terms of bandwidth, in terms of capacity, everything. And the second part is there anything more we can do with the storage in order to help these AI applications? And certainly both these angles is something which I will cover in today's discussion. Okay, let's get into a little bit more serious stuff. Okay, so I just wanted to set this context that yes, there is a massive amount of data that is available today. It's estimated in the range of 150 zettabytes by 2025. So if you do roughly 23% back, maybe you are roughly in the range of like 100 zettabytes today. That's quite significant in terms of the amount of data that we have. But again, this data is only in representational data. Now, who has what kind of data and where the kind of analytics is used is something which we can look into some details and see how it is, right? But the sheer thing is, if you look at the different pillars of the infrastructure, which is the storage, compute, and the network. If you look at storage, storage has been always making its first class entity as a capacity, right? So its goal to look at is, how do I accommodate this volume of data? Whereas if you look at compute, the compute would have always said the thing, how fast I can compute, right? So the other metrics for this to if you look at the computes, is actually speeding up the computes, whereas in the storage, the first class thing has always been in order to focus on how do I accommodate this kind of a data first, and then probably focus on how can I speed up the other operations. It's not like the other thing of speeding up how to read the data is not important, but first you have to address the basic necessity, which is basically the capacity, right? So it's always the case that you will always look at how the capacity has been going from one generation to the other. Now that's one case of it. Now again, the whole thing of the generation that has started with a new thing, which is a generative AI. Now this seems to complicate it slightly further, not from the perspective of anything that it has to do differently, but the sheer demands that it has brought into storage. So we'll talk about what is a new thing. So just for the purpose of this conversation or the discussion, what I'm going to do is I'm going to call the traditional MI, which is primarily used for different kinds of use cases, as traditional. And the analytics, which are the newer ones, which is actually working on the generative models, those I'm just going to call it as a generative AI. Okay, this is just for the purpose of mere in this thing. Now let's look into what is the changes that has happened in the spectrum. This is just a primer to what it is. So if you look at it today, earlier in the things, what we used to do is you had a set of data, you would create a very task specific model, and you would use, train them, retrain them. And it's very specific to that data set. You're learning a specific function in that thing. So that was the yesteryears, and most of the models today also continue to do this, right? Now, there is also similar things like you wanted to pre-train once, and then you wanted to fine tune many times based on how many ever domains you wanted to adopt, or as much specific examples that you would have, right? So there are a lot of examples in the domain of computer vision and NLP where you would basically have the base model, and you will also have a domain adaptation in the first one, and then also a task fine tuning on the other side to create a new model that would be doing. Now, on the other hand, the current ones basically talk about the foundation models, where probably you look at, you have these large models that has been already trained in the corpus data. But again, I'll come back to this thing, whether it is a load on the storage or not, because even training these data sets and the huge data set and creating these models are also storage intensive operations, right? So it doesn't come devoid of storage itself. So on the right hand side, you see this foundation models, which is basically you have the large models, that is the base FMs, and then you basically talk to those models using prompt, and as much context you wanted to build, you may probably wanted to build as part of this prompt and put it to the base model for having right questions, right? So here also there are adoptions like how you can adopt these models, how you can fine tune these models for your customized environments, customized data sets, right? So this is just not only the data that has changed, there's also massive change in the way data is being used for different use cases. Certainly, every segment in this thing has its own use case. It is not that once a foundation model is available that the traditional ML becomes obsolete. There are its own use cases which it performs well. So all of these are going to be living for some time until one of the other beats and says that yes, we don't have to look at others because we have the superlative models available for all kinds of data sets and all kinds of use cases, right? So until such time, all these three spectrums are still going to be alive over there. Okay, now coming to this thing, where is this interaction with the storage, right? So as the first question that we looked at, right, that there is this massive data, you need to read the data first, and then you want it to do. If you look at the pipelines that we have, I have given an example on the left hand side, which is a traditional ML, and on the right hand side, a generative world. In the left hand side, you will see that the traditional way of doing is you just ingest the data, you transform the data, all kinds of transformations could be done, like you prepare the data, cleansing, validation, all those kind of things. And once you have the prepared data, you could either do a model training or you could do an inferencing based on what stage you are. And on the model training, if you have developed a model, you put it into a model catalog, and that's going to be read, right? On the right hand side, the current thing is in the generative world, there's already large language models available to you. So what you do is on the user side, this is mostly on the application side, not on the training side. You basically use your prompts, which is primarily a bigger version of what we call as queries. And you create this embeddings of those queries because it's going to be in the form of natural language. You use those prompts. And you're going to search this vector database, which is going to have a vector of all these documents or the knowledge that is available, and you're going to put those existing knowledge in the form of the embeddings in this vector database. So you're going to search your prompts in this thing, gather some context around it. So you're going to build this context, which is primarily looking at something like similar documents. You take those relevance documents, you create context aware prompts, and then you're going to use your language models to answer these results, right? So now if you look at both these pipelines, there is a good amount of interaction with the storage, right? So storage is becoming indispensable because when you have the data, the ingest part of it is going to look at, reading the data multiple times. Then there is every transformation stages. You will basically read the data, you will write into it depending on the kind of operations you do. You could do some of them in memory, but if the data is large enough that your memories are overflowing, then you have to still spill over to the disk and start doing it, right? And also if the stages are running in a distributed fashion, you still have to go to the storage, read it and write back. So everywhere in this pipeline, you will see that there is an interaction with the storage, and in the similar fashion in the generative world also, every stage over here that you see, it has an interaction with the storage. Now, this is very critical to understand because you could do fancier stuff with faster computes, throwing a lot of computations as long as your computes are growing. However, your interactions with the storage are also critical because unless the data is made available in certain fashion, even if you read once and do it, that is also going to be critical in order to help you speeden up your entire pipeline itself. So storage becomes indispensable. It is important that storage helps the AI applications to accelerate in whatever form we could do, right? So that's the background of where is the interaction of the AI ML or the generative world with the storage, and with that context, we are going to set into a couple of things, right? So do we see any issue at all, right? I mean, storage seems to be like, yeah, there's a big amount of data, we read that data. So do we see any issue with that thing? Some of the experimental workloads that we have done, uh, it's not even in the petabyte scale, but if you have looked even in the terabyte scale, so our experiments within our lab indicates the following proportion, right? So when we read the data and do certain operations, which are primarily these long aggregates, it's a simple transformation operation on the data, you would see that this is a split that we observe, that your CPU runtime is roughly just about 40%, while your read and write times are about like 60% of the time. So here clearly the bottleneck is in the storage as opposed to the CPUs. Now, I just want to make one caveat over here. When people report numbers on, what are your throughputs, IOPS, and all these things, the experimental setup is also very important. There could be an experimental setup in a different thing where you just throw so much of cluster nodes, you're accessing them parallelly, all those, the kind of speedups you could do, those numbers would be completely different. So it is important that people understand under what setting the measurements were done so that this could be used in the appropriate settings. So that said, probably it is important to see that there is always a read and a write time to the disk, which is crucial, and certain times the read and the write times must be much more than some of the computations you would do. And those are situations when you see that the storage becomes the bottleneck. Okay, so there is a problem that we need to address in those cases. Now, I just wanted to give you an example with what is the data set looks like in a generative AI, because the numbers that you see here, what we have done is primarily with traditional record-based data sets, and we are looking at what's the time that was taken for a read and a write operation. But if you look at what it is here, these are all numbers purely taken from how the models were trained from the Wikipedia source. So if you see over here, it's not a small database that we are looking at, right? So roughly, if you look at it, if you are looking at 100 plus billion tokens, it could take about 1 trillion tokens of text in the pre-training itself, right? So if you, and tokens is basically a delimiter. When you have a sentence, you divide it through a delimiter. It could be a simple space, and if those are the kind of things, we are kind of looking at quite a big number of tokens, and those tokens, reading and writing them, are going to be a big issue, right? Even in the training phase. So it is important that we understand that storage becomes an integral part of the AI workloads, and it is important to see what we can do in order to enable AI to go faster with the storage available today. Okay, so yeah, so I think I've set the sufficient context to say that yes, storage is critical for the AI workloads. Although, the distribution of the computes over the storage is important, because we need to understand whether it's more reads or whether it is more choking on the compute side. So, it depends on workloads to workloads. Irrespective of what it is, if you have a data size of X amount, you still need to read that X amount of data set to actually perform your ML operation. So in that context, it is important that we do this. And before I go further into it, I just thought for those who are beginners that there are a few metrics that we may need to understand. And once we understand those things, it's also easier for us to follow what would happen in the subsequent slides, right? Because these are metrics that are commonly used in the storage world. So the first metric what we look at is the latency. Then there is IOPS, then there is bandwidth, and the latest entry into this segment is the power, because there's been quite a good amount of focus on energy consumption or the power consumed, and then probably looking at how can we make sustainable data processing, right? And what is the storage role in that. So these are four metrics that we can look at it. And on the right hand side, I've given a few examples of how primarily it is computed. So if you look at a storage, typically a storage has a controller to which your request comes. So if you have a host could be just a VM over here. So if you just assume that these are VMs, each of these VMs could just give you some kind of an request, and that request could come to the front end of the controller. So where you measure the IOP is at the controller side and not necessarily at the VM side, because VMs are individual VMs here. So the reports that you would see for a storage actually comes from the front end side of the storage metrics itself. But on the back side, you would see that those numbers could be quite different, and you could actually be accessing different kinds of disk drives. And based on what you would access, the numbers at the back end could change. So you are basically looking at computing the IOPS in the front side of the storage controller itself. The similar way is on the latency. So latency is something you have to aggregate the latencies. Like say, for instance, if there is a host that writes certain data, and the storage controller takes, say, for instance, 1 millisecond to do that, and storage controller could do certain operations with that call and it takes, say, 1 milliseconds, and in the back end it probably sends it to another one which actually takes, say, 0.5 milliseconds. So it is a cumulative value that you would see at the host. So typically you could measure your latency either at the host level or at the storage level, depending on where you wanted to report it and where you basically wanted to look at it, right? So these metrics are critical, and every time we are going to look at some storage systems, we are going to always talk about these metrics and how these are going to support our AI workloads. Okay. How are we doing in terms of storage capability going from one end to other end? So if you look at it, this is some metrics that is available over there. So we are actually looking at the number of terabytes per drive, which has been moving from 10 to 12 terabytes. So which means if I have one disk which is available, it's going to actually support you in the order of 12 terabytes. This is also because of the compaction factor that, from what we used to use a floppy to what we can come over here, the compaction actually helps in putting more data into the system itself, right? So we are doing pretty good over there in terms of compaction. In terms of storage installed base, you will see that there is two versions typically used, right? One is the SSD or the flash version of it, and the other one is the HDD, which probably works more from the magnetic based on magnetic things. So in that also, if you see that thing, the number of drives that's being used is quite in the order of 120 million drives. So when we talk about sustainability on all these things, you will probably look at all these numbers becoming relevant over there. Now, storage, are we doing enough to give all what is required? We can look at some of the three metrics, and if you look at some of the systems, what is available today out in the market, they're pretty much doing very good. In fact, I would say, like say, for instance, arrays could go up to 3,283 terabytes, and it can logically expand to something like 10,000. TIB is basically the base 2 version of the terabytes, right? So you could go up to that, and your reads are actually milliseconds, which is very good because we had started with something like milliseconds and then it's come down over here. So 75% of your read and writes could be in the order of 250 milliseconds. So that's pretty good numbers. And also it delivers the IOPS in the order of 2 million IOPS, right? So later I have a slide to explain how this IOPS would help. So this is also significantly a good number. And if you look at it, the way storage has evolved over time and today what it is, I think it has the kind of capacity as well as things to basically support AI workloads. Yeah, so even if we have this, is there anything that we can do better is a question that we are asking through some of the work we have been doing, and we can see how that can help, right? Yes. So given that, the storage has seen a sea change from, what it has started to what it is today in terms of capacity, in terms of IOPS, and in terms of the latencies, is there still anything that we need to do? It turns out that there are three dimensions in which there is a scope to improve, right? So one is, I think, with the amount of CPU speed, to catch up with the CPU speed is a different issue altogether, but you need to still look at how we can support that kind of thing. Like, say, for instance, if you're having a rack which is having your GPUs attached with it in parallel, perhaps you may have to look at in the order of delivering 1 terabytes per second, which still is a long way for us to go compared to what it is if you look at just one storage array, right? But of course, you can actually parallelize those things, and then you can do a cumulative number, and then you can you can throw up those numbers over here. So there's quite a bit of thing that you wanted to do at speed. On the second thing is the power. There's the power also consumption is quite going higher with these things. Like, say, for instance, you're actually using in the range of like 500 watts. So is just one enclosure that is available over there. So you need to do more to conserve the power too. And on the third thing is primarily you are looking at the cost. Like, one can look at, if you wanted to store like 1,000 terabytes of data in the cloud, you're actually looking at a bill of like $1 million for a year, right? It's still expensive. So far what we have seen is primarily we looked at how AI interacts with the storage. There is an indispensable need that storage is critical. And because the volume of data is available in that, at least one read you have to perform, and then you can talk about all kinds of optimization you can do. And then there is this second phase of this, what we talked about is the metrics that we look at. And we also said that the current storage systems that we have do give us a certain benefit of the capacity, speed, and the throughput. But given those things, is there anything else that we should look at? Is, if you look at, there are still three segments that we can work better, because it still doesn't turn out to be the most optimal available. Like, say, for instance, $1 million for a year for 1,000 TV is quite a good amount of things. So there is a necessity that we should look at how can we optimize the cost, and also looking at the power consumptions. How can we bring down the power consumptions of these things, and how can we basically look at increasing the read bandwidths of the storage. So these are three key things that we should always look at and see what is that we could do best, right? So I'm going to put my opinion and theory over here, and always certainly we can always look at discussions around those things. And so we are looking at doing these three things. One is we wanted to become faster, cheaper, and energy efficient. And to me, it looks like we have two dimensions of doing it, right? So one is, let's look at what happens when we increase the IOPS, right? So there's two examples what I've taken, which is a similar one. Let's say two systems, one of them is giving us say 10 IOPS, and the other one is giving us say 100 IOPS. So if you want to do a read of a 3 megabyte data, and 128 kilobytes is a read that you're looking at. So essentially, to read this data, you would need about roughly 24 reads. And if you want to do this 24 reads, if you look at the seconds, it would take roughly like 2.5 seconds, right? Because I'm just assuming that you could do on a full throttle 10 IOPS per second. So if you look at this, you would roughly take about 2.5 seconds to finish this entire job. Now, with an increased IOPS, like say 100 per seconds, it's a simple math that if you have 1 second, you could actually perform say 100 IOPS, you would actually consume less than 5 seconds, right? So can we keep increasing the IOPS more and more and more in order to actually reduce your time that you would access it? Certainly, there are limitations for it, because you still are constrained by the technology that is available. Although on the technology side, there's a lot of research going on to improve these numbers, right? So let's look at an alternative approach. Is there any other way by which we can primarily look at increasing this? So this is where most of the work that we have been doing in our lab comes into picture. So we looked at, is there every data that is available on the system, which is probably important for the insights. So it turns out that there is good amount of data that probably falls into this category of irrelevant data sets, because they probably either are not giving you any new insights than what you have done. So essentially we looked at the version of what I'm showing over here, that if you have a proper data lifecycle management and understand the relevance of data, and you start training with the minimal data set that is required to get that insights, you could actually do lot more in terms of. So what we are doing is, if you go back and look at it, so I have only two options. Either I look at increasing the speeds of the storage itself, or on the other side, I look at reducing the amount of data that you can process on this thing, so that you could basically go faster on doing it. And can we take the second approach? Certainly yes. There's a lot of work that you could do in order to looking at. First of all, the term relevance itself is quite an ambiguous term, which requires a lot of understanding of the data, understanding of the model, understanding of the domain. How can we look at, a striking balance of looking at the relevance of data and using that for optimizing your storage requirements? Then the second thing is, we need to get used to the mindset that start training with a minimal data set. Certainly, these are more appropriate in the context of traditional AIs than with the LLMs and the generative AIs. We can talk about, those as a second part of these things. But primarily, if you look at focusing on the traditional AI, which consists of all the applications which are domain specific and task specific, so there is quite a good amount of training that you should look at with the minimal data set itself, right? Yeah. So our approach has been, while the storage continues to do its infrastructure improvements in terms of, how, what's the material it could go, what's the compaction can do, and all those kind of things. The second aspect of what we are telling is that see, all data sets perhaps is not required for you to get the amount of insights. Certainly, if you have unlimited compute and unlimited storage, you can go ahead and do that kind of a thing. But if you wanted to look at optimal way of doing it, the approach one should look at is to understand the relevance of the data and how do we actually optimize the storage for that. So with that, I'm going to start with a couple of work that we have done. And this work embodies many of the individual experiments we have done, plenty of experiments done on customer data sets as well as publicly available data sets, and very small options of looking at data and finding out what relevant data is available and trying to exploit that property of data to see if we can actually reduce the amount of storage requirements, or even increase the efficiency of the reads and the writes, not purely from the storage perspective but from the application perspective, right? So in that, I think we have categorized all these kind of work into three different things. So the one is there any approach by which we can actually reuse some of the insights that we had obtained from the earlier runs? That's one body of work. The second body of work is, you look at the data and the characteristics of the data, and is there any of the facets of this data set itself that you could exploit in order to reduce the data? And the third part of it is primarily looking at similarity. And I think similarity is not something which we are talking today. There's been a decade long research on similarity itself. So that is something which we will also look in detail here in our talk today, to see how this similarity properties can be exploited to basically reduce the amount of data that you get processed with this. Okay. So I just wanted to check if there's any questions so far, if anyone has, and then we can take a couple of questions and then we can go back. Okay, I see one question in the lab setup. Do you prefer cloud or SSD or read for read write large data sets, right? Okay. So I would answer this in two parts. And one is, first of all, it completely depends on, again, primarily cost as one factor, and then your numbers which you are looking at for throughputs, the IOPS and this thing, right? Certainly being on the cloud is advantage in terms of expansion, because you could basically go from a smaller and then you can keep scaling as you want. So that flexibility is something which you would get on a cloud readily, but on the kind of an on-prem setup where you will go and put your boxes, the scalability is quite challenging, because if you want to add anything, it's then results into a purchase of things, right? So from the management perspective of these things, it's purely you would prefer to have a cloud rather than giving an on-prem. If you're looking at just throughputs and looking at the IOPS numbers, certainly you have actually mentioned an SSD. It would be far superior than actually having something on the cloud. In fact, there are metrics available, which I also had some slides, but I think I moved it out of it just in the interest of to keep it thing. So you would see this numbers. And if you're looking at SSD on an on-prem setup, I think that would be the best to go for your read write, right? So it just depends on how you would want to do. And also the operating model is one of the criteria. Like say, for instance, you may look at storage as primarily an upfront investment that you would like to do, or you may want to do like an operational model, like you just pay as you go. So you may not want to spend the capex kind of a model is not appropriate for your lab, for your setup, right? So if that is the case, then it is certainly better to go with cloud rather than going with this thing, right? So some of the experiments what we have done and seen, you wouldn't feel you're doing too bad on cloud in terms of IOPS and things like this, because for some of the nice things that can happen offline, like say for instance your trainings, and also inferencing at certain things which are not online, those things are, you know, what we call as a backend systems, right? So those systems which can go slower and doesn't matter how much time it takes, then you could prefer to go on a cloud. But if you are looking at something like an inference that to happen on a faster mode, then probably you could look at using something on an on-prem SSDs, right? So I wouldn't say that it is just one criteria that defines which of these you wanted to pick up. There is a multitude of dimensions. In fact, my last slides, I do have a set of questions that will lead to picking up what exact kind of metrics that you should basically do to pick up these. And certainly those things would drive, and certainly cost is a factor, scalability is a factor, and your numbers. If you're looking at giving more weightage to some kind of go as you do your work, I mean, if you prefer to have those kind of model, then certainly cloud stands first when compared to your SSDs. But if you're looking at purely throughput, reading fast and all those things, certainly your on-prem SSD is far better for your read write large data, right? So that would be my answer for that. Okay, I hope I gave some insights to it. So we'll come back to questions if there's anything more. I see a lot more questions, but we'll come back to it at the end of this thing. So, right. So I just wanted to recap what we are looking at. Is storage doing good? Yes, it's doing good. But is it doing? It could do better. Yes, there is a lot of opportunities to do better than what it is doing today. Specifically in these three things. One is in terms of speed, power, and cost. And in order to do these, there's only two angles, right? One is either you focus on infrastructure and make them better, or the other way is there a way, because of the nature of the AI, that it requires a few information relevant data sets? Can we actually look at trying to reduce the amount of data set that we can process? And in that mechanism, can we actually have better performance from the storage itself? So that's the kind of question we are looking at. So I'm going to go and talk more about what's the kind of things that we have done, what's the kind of looking like. And before we do that, I just wanted to have a few observations and a few ice breaking sessions over here. So I posted a data set over here. So just assume that this data set is actually 4 collections in a day, and it's just talking about IOPS of storage, right? So I've given for 3 days over here, and I wanted you all to talk about what do you observe from this data set? I mean, anything that you observe, I mean, characteristics, you know, what do you first thing that comes to your mind about this data set? If you could just post those, probably we can have some conversations around that. Anything that you observe with this? Yeah, maybe we should have at least 1 or 2. Okay. Okay. I see answers like, okay, day 3 has less IOPS. Well, nice. Day 3 variations are less. Okay. Anything else? Okay, increased usage. Okay, that's, I think somebody has done an AI there itself. Similar database. Okay. All right. I think Diwakar got it right. So the variations, it's just not for day 3, right? So all the 3 days you would see that the variations are very less, right? So it's just in the order of like 1 or 2. So what we could say is that in this data set there seems to be very less variations, and as well as maybe we can say that the data set is similar, right? So that's the, yes, I think somebody got that. So it's IOPS is similar. um, I would say in almost all these things. We'll come back to it. I mean, how much is a similarity and things like that. Okay, I'm going to post one more over here, and if somebody can talk about what do you observe between, not between these 3 diagrams, but between the 2 sub images within the different categories, right? What do you observe over here? Any observations on this? Okay, I have one answer. Colors are different. Okay, and then there's one high similarity. Right. So except for certain features that is available here, I think we got some correct answers too. So it's primarily looking at very high similarity between these 2 things, right? Now, the point that we wanted to answer is, now if we have similar data, is the first one, can we do a few things that we can optimize? That's the first question we are going to ask. The second thing is, if there is similarity, can we say that there is lot of data sets that are actually similar in nature, so that the first optimization that we are trying to do on the similar data sets applies to this large corpus of data, and because we are applying it on the large corpus of data, then probably we'll be able to optimize the amount of data that we are using for computing this thing, right? So the observation is correct that all of, I think many of you have got it right. So there is this whole concept of similarity with the data, and it turns out, and from our experiments as well as from many of the other research that's been done, that there is quite a bit of similarity that you will see in the data, and there are reasons for why it is similar too, which we will also see, right? So right, so you would see that the reasons being, like when you look at repetition variation, like let's see, if you look at a sensor or surveillance or geosatellite data, the variations probably are very little. Data generated by similar sources, like say for instance, if you look at you're monitoring say an heartbeat of drivers of the all the taxi drivers, right? So if you do such as application, so you would see that your source, there is very similar or very little variation in the data. So the data that is getting generated is almost similar, right? The results of similar computations on the similar data sets. So if you look at it, you would see that there are reasons why data sets are similar, and there is and these data sets are quite huge in number. I mean, there is a good corpus of data sets that are available. We'll also talk about those data sets, what we have seen in this thing. Specifically in, if you look at the images as well as in time series data sets, you will see that there is quite a bit of similarity that you will observe. Now, the question is, can we exploit this similarity of the data sets to do certain optimizations, right? So what are the optimizations we could do? I'll come back to this. This is basically the kind of things. Right. So I'll come back to those slides slightly later. I just wanted to little fast forward in terms of what we could do. So if you find that there is a similar data, the question you wanted to ask is, can you reuse the output which was available earlier, which means the entire kind of things that you will do, your ETL operations to applying the models to do it, you could, is there a mechanism to bypass this thing, right? And the second thing that you could do is even for model trainings, although today model training is done when a new data set comes, and if you or you basically see that there is a wide drift in the kind of output that you would get, you go ahead and train your models. Is there a way to early identify that this doesn't require any model training, and therefore you could save your computes on the training itself? And then probably you could also look at using different kind of tiers to archive this data sets, right? So that's probably the kind of different things that you could do in order to save it on the storage. Now, this certainly would reduce your compute cycles as well as your interactions with the storage, because you're going to bypass those stages over here. The question is, who's going to do the similarity? And the hypothesis over here is because data is 80% of the time available in the storage, and most of your operations are moving from reads and writes within the storage. The one that understands the flow of data between the different reads and the writes is perhaps the storage, and therefore can we make a similarity as a fundamental unit of the storage itself. So this is something which we have been actively looking at, what are the kind of features that we should push which might be friendlier to AI applications into the storage. Therefore, those applications which can gain from actually having similar data sets can be identified early on by the storage itself, create a metadata of that similar data, and the applications can effectively use it. Okay, so I'll go back and look at what are the examples we have done and how we have actually arrived at that there is a good case of actually creating this feature as a fundamental property of the storage itself, compared like every other storage features such as dedupe and compressions, right? So today, if you look at every storage offers you the dedupes and the compressions out of box, because that has become as a fundamental property of the storage itself. So when you look at similarity and we look at what could similar data sets do it, you get a bunch of benefits out of it, just not only from the storage perspectives, but from others also. Like say, for instance, one of the things is the power saving, because you are primarily bypassing a lot of ETL operations and lot of the trainings or the inference that you could do, and primarily you may readily use one of the outputs that is available, right? So you would accelerate analytics by skipping and getting to the output much quicker in the life cycle of the pipeline. The second thing that you would get is to optimize the storage, because you could also now say, hey, these are all similar data sets. And if you could identify at the time of ingest itself, now you could say that these data sets would be assigned different values, and probably some of them could be moved directly to lower tiers, allowing the storage for more better data sets to be used, right? So that's one thing that you could do. You could also prevent the generation of nearly same data across workflows. So this is something which we have also exploited, where we understand the AI pipeline, understand what is the output that is coming out of each ETL operations, and can we actually prevent those creations, because you have already understood that the data is similar to an existing run that has already happened, and reuse those sets, right? And then you don't have to worry so much about model retrains, because that pipeline can still work. But what you're doing is, instead of doing it after you do identify model drifts and things like this, you're pushing much earlier in the life cycle of the AI pipeline, where you could identify that the data is similar, and then you can knock off those things, right? So you could also reduce the data movements, because as soon as you identify, you can actually put that as a similarity check within the storage itself, and then you can move it down to different tiers. So you get all these benefits when you actually identify that there is a similar data sets. And our observations, we have actually looked at a relatively larger corpus of data for enterprise data sets. Like we had looked at from 1,500 VMs. We look at about looking at prediction, kind of an forecasting applications, and we have looked at how this data actually behaves from each day-to-day operations, and also how it actually runs over a period of time. And then we have observed that there is quite a bit of similarity that you see in this data sets, right? So you could apply a wide variety of similarity algorithms, and on the simple data set, we see that some of the times your similarity is as high as 80% of the thing. But the question is not whether the data is similar or not. The question to answer is, if I have similar data sets, is there a mechanism to reuse the output that has been generated by a previous thing? So that's the crux of this thing. And if it turns out that the application can tolerate a similarity as high as 80% and doesn't change the output of your model because the performance of the model on these similar data sets are same, then maybe you could just bypass all those kind of things, right? So that's what we are looking at over here. The second example we have also looked at is, yeah, so I think this is one example. And the other example that we recently looked at, how the data set is showing similar data sets, is in the form of, again, another forecasting application using the IOPS data collected from different VMs, and that is again an example where we say that there has been a good observation of about 80 to 90% similarity, and if the data is similar, now it just leaves us to understand whether the similar data sets makes sense in the kind of models that it is being used, and if they are producing similar results, then why not bypass all these kind of computations, right? So we have done pretty good amount of experiments. So this is the example that I was talking, where you have multiple ETL operations, and you do, what we do is we do two plugins, one primarily to track the lineage of this data, and second is to primarily compute the similarity algorithm, applying a similarity algorithm on it. And at a stage, if we find that the output of the ETL operation is same as any of those that had a prior run, then we primarily tend to bypass the entire stage. And if that happens in as closer to raw data sets, then you are actually bypassing all the ETL operations that you do in this thing, in that pipeline, right? So that's quite a significant amount of saving that you would do, both in terms of accessing the storage as well as how much of the computes that you would do. So so I'll move a little further in terms of, yeah, these are all examples. So if you see a similar data set, you can seamlessly bypass the remaining steps. So how do we do is we plug in a lineage mechanism into the Spark, and from there we trap the data set that comes into it. We look at what is the input that has come and what's the output it has come, and then we compare those with the previous runs, and we see that if it is similar, then we actually don't execute the pipeline itself. And by doing that, we have shown that we could actually go in the amount of time that you would see, what's the kind of thing that you would see. We have got quite promising results in terms of actually saving the time that you would do with the different stages in this thing, right? So so this is one promising area which you could do, and what we have shown actually in real setup is that you could actually speed it up to 97%, specific to this kind of the workloads we have. So two criteria that are important in this thing. One is how much of similarity you find. The second is, even if you find similar, is your output of the models changing because the data set is similar? Then if it is not changing, then probably can you reuse that the same output that you have got. If it is forecasting, probably you're just telling that, you know, what you forecasted yesterday is the same as the forecasting today. But of course, if there is a change in the data that is detected upfront, you still need to pass that and do the new forecasting for the data sets, right? But having a speed up of about like 97%, because if you bypass and if your answer is readily available and you're reusing that, that's quite a significant promise compared to what you would basically do passing through these stages, right? So this is one set of work that we had done, and we see that it's very promising. And in the similar lines, we have another set of things which is called as reusing the models. So if you look at the model training, that is also a computationally expensive one, and the model training requires that you basically read the data which is available from the storage. There's no bypassing that because models training requires the data and you need to actually train it, right? So that's an expensive operation. So typically what you do is basically, how do you retrain the models is you either look at how badly they are performing with the real data set, because if you look at the drift and when the validations happen through the real data, you would do that. Or you could actually, in the real settings, like some of the things that we do, we actually run as soon as a new data set is available. Many times this is actually repeatedly done in order to make sure that you are not throwing any number to the customers different than what it would have happened in the recent data sets, right? So as soon as a new data set arrives, you practically run the model training to make sure that you read all that new information that has come and then you do it. Now here also, if you look at, I'll come back to this thing. So intuitively, if you see that thing, that if you have percentage similarity over here, you can actually save the training cost either in terms of CPUs or in terms of reading from the storage. So you are essentially having an opportunity to save the kind of storage calls that you could make in this, right? So come back to it. How do we say that the similarity is going to help? Again, you need to understand how the model operates with that kind of a similarity data set. You need to do at least a couple of runs to understand how the model is performing with respect to it, and if it is same, then probably you could go ahead and say that these models with the similar data sets are performing same. Therefore, when the similar data set comes, you are just going to bypass the training itself. Do we know that upfront? No, you would not know it upfront unless you do a couple of runs, and you also have to keep a tab on how that dissimilarity basically is important for the models, right? Like say, for instance, if you have an example like this, this is just a small this is a very popular example taken from the GANs, where you basically have an image and you just add a slight perturbation to that thing. You basically end up getting a different kind of an image. At least as far as the AI model is concerned, it's different. So you need to understand whether this dissimilarity is a problem for the model or not, and you would be able to do that only if you iteratively do a couple of runs, which is what we do. We basically run a couple of times to understand how the model is performing with the validations, and when you're confident that your data sets are not creating too much difference in the output for the similarity observed, then you primarily kickstart your models to basically not to be trained. The advantage of this thing is you're pushing too early in the cycle of the pipeline. So with that, you could actually try bypassing the stages of the model training, thereby gaining both on the compute as well as on the storage point of it. So this is the other work. So we have done a quite extensive study on this thing, using a good number of installation bases from the customers, as well as using different kinds of models. And we see that these two things quite pretty much, if you reuse the models, you are not performing too different than what the model would have done if it has actually learned from the new data sets. But you basically are saving on training of the models by observing it right up front in the AI, in the cycle itself, rather than pushing it late in the cycles. Okay. Yeah, so these are some of the things. Like we had at least about like 85% of the time we were able to reuse with a very less difference in the variations that we have observed. So it's quite probably a promising area to look at. There are other open questions in this area that one needs to look at. Like say, for instance, the kind of dissimilarity that is available, is that something that is going to affect the model performance or not? So that is something which somebody has to observe over a period of time and come up with opportunities to say where you can exploit that. So yeah, so what I would do is, I think all these information is available. We have published papers on this thing, which we will share it. And in the meanwhile, I'll take a couple of questions in the interest that we may or may not have some time at the end, and then I'll come back to the remaining portions of the slides itself. Okay, I'm going to take a few things. Okay, so there's one question from Supriya which talks about if there is a network attached or in SAN configurations, is there anything better suited for AI applications, and if so, why, right? Okay, so let's understand. See, there are three components to AI, right? One is you definitely need the computes. The second thing is you need the networks, which is primarily looking at either interconnecting the computes to the networks, or to the storage, or within the storage itself, because if you have multiple boxes, there is definitely going to be an internet connect that plays an important role in connecting these things, right? So so irrespective of what the configuration you have, if you look at your your storage could give you the required IOPS for your applications, which one has to determine what is a suitable IOP for my application, which I do have an exercise at the end of the thing, which we can come to. Then it is very specific to that domain or that task or that model, what is the kind of requirements and whether that is suitable for it. So as I said, the settings in which you will measure whether this is available or not is straightforward, not an easy task to say, okay, if I do this, then I'm going to get this kind of a performance, but it purely depends on the workloads and how you would actually get the IOPS. So it would require a couple of iterations of running your models on these things to understand what is your requirement and then tune towards these two things. So I wouldn't pick up between any of these things as a straightforward thing to say that this is better suited than the others, right? So how do storage solutions ensure data consistency and integrity when dealing with AI models that may be distributed across multiple servers or clusters? So if it is so, I mean, the one answer that I could do to that is basically your consistency and integrity are left to your applications to deal with that. So your applications should ensure that the data is consistent and it has the required integrity. It's really not pushed when you push it into the storage. The reason is because now when you talk about distributed storage, unless you have a middle layer that is operating and has the visibility across these different storages, it's quite difficult to basically do it at just one storage level, right? So you had to push it to one of the layers above it to actually take care of it. Say probably a data management layer which sits very close to the storage, looking at it in order to get this consistency and the integrity part of it, if it is across different servers and clusters. Yeah, with more and more input parameters, how do we find similarity? Similar patterns will be difficult to find when considering more input. Yes, I'll answer this question because I think one of the potential research areas to see is what is the overhead of doing the similarity itself and how is it going to perform over a period of time, right? But now one thing which we should understand is when you talk about similarity, similarity is purely a computational exercise, right? So you could have a huge amount of data and probably you're looking at doing it and pushing the compute and finding the thing that it is similar itself as a computational exercise. So you are pushing from storage bottleneck to an compute bottleneck, but assuming that computes are much more faster than storage, then you had conveniently pushed that problem to the storage from the storage to these computes itself. Now, yes, it is an intensive thing, but if you look at the kind of compute, it's a very simple thing, right? I mean, if you look at the Euclidean distance, it just finds out, a value a minus value b divided by uh, the formula to compute that things are not so cumbersome, except that it is again dealing with the data in large. So it is yet again another set of problems that we have, that whether we can actually find an easier way to do similarity if the parameters are large. Maybe we do some kind of a sampling to say, okay, we will look at these samples which are representational samples, and from that can we just look at similar patterns, right? So that's one way we could even look at reducing the size at that stage. But again, when we talk about similarity itself, we have pushed that into the space of computation rather than pushing it into the space of storage, because as we say, the storage is going slower than what the computes are. So you may still be doing better off doing similarity than actually doing multiple read and writes through your ETL operations. Okay, so we have done some exercise, identifying it, and we have also left certain portions of that as a research problem to be addressed, that how much of similarity is beneficial and whether it is basically going to be again an issue to do similarity when compared to, so what's the overhead of doing that similarity, right? So we have done some exercise which I'll cover, and there's some things which we need to leave it as a research exercise. Okay, I'll go back to the slides, and let's keep moving forward, and then I'll come back and do it. So just to look at the recap so far, right? So we have looked at similarity as one domain. There's quite a potential that similarity provides. Similarity is not something which we have started today. It's been in the decades since the data statistics time. So it goes at least a couple of decades back, looking at how similarity plays an important role. And the only thing what we are looking at is we are actually trying to see if we can exploit that similarity in order to reduce the amount of data or the computations that you could do for the AI to process, and it seems to be that it gives us some significant improvements and a promising area to look at. Okay, so that's what I would say. And we do look at the other two things, which is probably reusing the insights and the data facets itself to reduce the data, right? So let's move on and look at what do we mean when we say reusable insights. So again, if you look at the operations, like say for instance, if you just take one of the forecasting algorithms, you are repeatedly performing the same operations on a different kind of the data sets, right? So what if it happens that the intermediate stages of the data that we produce are actually storable, which means this is something called insights, right? So if you have an insight which you can store, not necessarily the raw data of it, and if there is a mechanism by which we can say that this data relates to this insight, then perhaps directly using that insight rather than again going back and doing the computations to generate that insight is a beneficial thing. Okay, so again, along these lines, we have done quite a bit of work, and what we see is if you actually trace your lineage and store it in the form of insights in this in the insights is yet another set of data for us, right? But it's more compact than the actual data, raw data sets. So if you go ahead and create this insight store where you just store the data sets, now when your data comes, if you can relate the data to this insight through your lineage process, then you could actually reuse these insights and avoid all the computations that you would do. And in that process also, you are actually saving all the three things. I mean, storage as well as this thing, as well as the storage access to it, and everything that comes along with it, right? Your power, storage, power, computations, and also faster access to your output. So along these lines also, we have actually developed something called as an insight store. What we do is basically when the native storage, the data comes into this thing, we basically, you have these read writes that is happening. We do a trapper, which is this insight runtime that we called it as. And as the data is being read by these different kinds of analytics, what we do is we basically go ahead and store these insights, which you see in the right hand side of it. And if there is any request that comes from the top layer, we don't even go to the raw data to do it, but we try to reproduce it from the insights that is stored, as long as you can actually relate the data that is being asked to the insights that has been produced. So with this kind of an approach, where we are saying that we should actually build more of insights as and store them rather than storing the raw data, you would see that you would be able to accelerate for many of the applications which falls into these categories, that there is a relationship between raw data and actually the average, actually the insights that is being generated, right? So typically most of these reusable functions that is happening, you would see that are actually those where you can exploit such an architecture. And even with this kind of an implementation, we have shown that you could actually accelerate the applications to a percentage of about like 50 to 60%, right? So this is a promising, yet another promising area to see how you can build that insight stores, how you can make the insights reusable rather than the raw data set itself, or working at the layer of the raw data sets. Yeah, so this is one area which we have looked at, and as I said, we can, there's been a quite promising in terms of developing that metadata for the insights and making that available to the application layer rather than dealing with the raw insights, raw data sets itself. The third thing that we have actually looked at is the data facets itself. Now, when I say data facets, data has several properties, right? So when we talk about the data quality itself, there are various characteristics of the data. Like say, for instance, the AI, one of the AI facets is to have the data balanced. The other is other kind of things could be data, how clean is the data, and how filling is the data, how suitable is the data. So those kind of facets are available. Now, one of the facets that we have looked at, and we have actually built a library of facets which can be reused in this data to identify whether this data probably can be simplified than what the actual data says, right? The obvious one such metrics that might come for any AI ML person is if you have a large number of data sets that's or at least the parameters that is available, you could basically look at a simple thing of a correlation, and you wanted to really pick up what are those metrics that are influential in your model rather than actually working up using all those metrics, right? So some of the exercises in our thing looked like we began with a large number of parameters, but if you look at really these correlations and other such facets of the data, you could really look at only those influential metrics to do this thing. And by doing this, you probably have looked at reducing the data size on which you are operating rather than basically using the large corpus of data itself. So here also we have had many examples where we have shown that if you make these kind of functions, such as what are very relevant to the AI, like say for instance you wanted to look at a mean of the data set, or if you wanted to do distributions, understanding the distributions of the data sets as a fundamental property of the storage, and the storage could do these pre-computes and keep it for you readily available, the AI applications can exploit these features to actually get a reduced amount of data and use it for training these purposes. So we have actually experimented on different kinds of data sets, and here also we have seen that given queries, if you have this analytics data management which we have built, and one that doesn't have this thing, we have actually shown that you would get similar results in terms of performance of models, but you have actually reduced the amount of data access to the stores and without actually disturbing the model performance itself. So this is also another area that is very promising in terms of identifying what features of data really influence the model and how can we actually derive those subset by making it as a fundamental property of the storage itself and actually use them to bring down the necessary data into the application space. So this is the third optimization we have been working on, and there's a good amount of promising thing that we have got in this thing. Again, I'll share those information available for these things along with the slides. There's also papers that we have done. There's also patents which are publicly available today, which you can read through and see some of the benefits we have listed over there, and what are the kind of functions that we are pushing down to this management as part of the storage layer rather than being at the application, because these are all common across multiple things, and making it as a common thing in the storage is very beneficial for many applications that may run on the storage itself. Okay. So these are kind of the things that are important in the other dimension that we were talking about. How do we basically look at operating on finding out the relevant data sets for the model, and how can we influence the storage, and the whole thing of finding these relevant models itself or relevant data itself, can we push that as simple functions in the storage as inherent properties of storage, which can actually help the AI applications itself, right? So with that, our series of different approaches, I'm going to come to an end, and probably I'll have a look at any more questions over here. And then I have one exercise as again an icebreaker thing. And when we are done with that, I think we can open up for further questions if there's anything else we can sort of conclude the thing. In the industry, in the process, okay, I'm reading out from Balkrishnan. In process industry, especially being thermodynamic in nature, and where gases like oxygen is involved, which keeps varying a lot, how can we do predictions? Yeah, I think this is a very domain specific question. I think we need to get this look at how your data set is, what models would fit into this thing, what kind of properties of data we can exploit. I think this similar like to what the bioinformatics people do in terms of looking at the domain specific data and identifying what kind of operations we can do. I think I would leave it at that exercise. If you would like to see that, probably you can connect with me on my email and we can talk about what data set is that and how we can go about identifying a few things around that. Okay, are there any specific techniques or technologies employed for optimizing storage of predefined language models to reduce storage overhead? Well, this is something which I think I have put as my last slide. So there is question of, I mean, how do we basically help the current current models to do this, right? So there is no straightforward answer to this thing because these are all pre-trained models that are available to us. There is, of course, a need to basically look at reducing the stress when we are using it, primarily in terms of how we actually generate the prompts, how many documents are we going to process in terms of generating nice prompts, how it's going to be useful. But on the storage of the language models itself, it's quite challenging to, or probably it's too early for us to, declare anything that, okay, can a subset of GPT 3 can actually be used for answering these questions, thereby, can we create mini versions of that thing? Those are all things which probably is something which we probably have to work on, and I don't think there is a readily available answer from the storage, at least from my perspective at this stage. So I would again leave that as one of these, what metadata of data of the storage can be used for prompts, or how can we reduce that overhead, is yet another topic that needs further exploration at this stage. How about explainability in dropping similar data sets? Yes, okay, right. So if you wanted to explain, and because the models are very relevant in the explainability, because you are actually making that as an inherent function of how the models perform, and then you wanted to explain why this model performed in certain fashion, it becomes a challenging thing for explainability in similar data. But what we could do is, say for instance, if you're reusing the models or reusing the output of an earlier execution, how different would be the explanation of that reused thing than with so now there is an extra dimension that needs to be understood. It's just not performance of the model, but you also need to understand whether the explainability factor also changes with respect to using the thing, right? So that is also something which we needs to be studied across multiple runs, and when we see if there is not too much difference that we see in the explainability, then probably we can reuse the explainability also. But that's a good point. I mean, I think it's something which probably we also have to take it as some feedback and look at if there is an active stage of explainability in your AI pipeline. This dropping similar data sets is relevant. I think one dimension we need to add apart from model performance is also to understand how the explainability is differing with different similarity metrics that we see, and if the similarity metrics is saying that, hey, models performed well but my explainability has differed, then I think that criteria still warrants that we just can't go ahead and reuse the output over there. That's a good take. It's a good point. Right. Okay. So I think I've almost covered many of the questions. So I'll come back, and I want to give this teaser on as a closing primer. So yeah, so I think the question is, how do we choose a storage? What is the kind of metrics that we would look at when we wanted to look at a metric? So here is an example of that, right? So let's look at, if I give you two systems, and I tell you that the two systems, one of them have an 5,000 IOPS and the other is 10,000 IOPS. Could you please let me know which one of those systems would you prefer for your thing? Right now, there's no other criteria. I mean, I'm just giving you, say, one with the lower IOPS and the other with the higher IOPS. Which of those would you prefer for your workloads? I mean, if you can just respond back on the chat so we could take answers from there and proceed further. Any guesses? Okay, so I think I get this answer. So the criteria that you have chosen is, well, if I give you one metric IOPS, and if you say you wanted to pick up, that's going to be the higher IOPS. Absolutely right. So let me introduce now one more metric. So if I give, it's just not IOPS that I'm giving you. I'm saying that yes, you have one with higher IOPS, but there is another dimension I have added called as response time. Now, if you look at this graph, which one would you choose? Any guesses from here? So essentially we are saying that you have a bigger response time, smaller response time with lower IOPS. If you're going for a higher IOPS, the response time is also higher, right? So, okay, second one, less response time, okay, same. Both will do the same IOPS, okay. I agree. Okay, let me add one more criteria to this thing. So the third criteria that I'm giving is I am not actually saying that in point time, this is a thing. So if I increase, if I actually tell you for different IOPS, you know, how the response time has been for one system and how the response has been for the other systems. Now I have added one more dimension to this. Okay, so for Jitun's thing, I mean, probably here it is very easy that it just looks as twice the thing, but probably, you know, if the variation is quite different, then the question could have still been relevant. Yeah, I agree with this example. It's turned out to be that after 1 millisecond, you will get the same thing. But let's look at this graph and look at how this is going to perform, right? I mean, are we looking at two systems? Is there anything that we can decide on which system we wanted to perform or which system we would choose here? Any answers? Okay, looks like a tough one. Okay, system one. Can I know what's the criteria you have used for system one? Okay, system one. Okay, very nice. It's a good observation that it's not having too much of variation or it's not increasing exponentially. So yeah, let's look at it. So here we have added one more dimension of this. You may want to look at the trend of it, look at how your IOPS are looking at, and then you may want to decide, you know, which of these systems you wanted to do, right? So first we looked at, it's just not sufficient to have IOPS. It is not sufficient to look at response time. You want to look at your trends and see how it is performing and then do it, which essentially leads to a very important observation that are you looking, what kind of workloads are you looking at? Do you want something on maximum performance? Then you look at on the left hand side of the thing and see which of these things are meeting your criteria. If you are looking for, okay, I'm not looking at that kind of a high performance thing, but you know, minimum performance requirements is on the right hand side of things. If your requirement falls in that zone, then probably you pick it up. So the 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 kind of things we are iteratively building is you need to know, understand a few metrics around it. On that metrics, you also need to understand where are you looking at that you wanted to have your application fall into with that kind of metrics, and then you wanted to pick up which system actually suits that and then probably pick it up, right? So I think one of the criteria that we applied here is you go ahead and put your acceptable uh, band kind of a thing, and from that acceptable thing you actually fit which of these things are, you know, fitting into it majority of the time, and with that you could actually pick up which of these operations looks at it, right? Now that said, now even in this diagram, like as what I see, some of the responses in this thing says that system one is more acceptable because you see less variation, and system two is higher variation. Even though system two might fall into an acceptable latency band, you may still prefer to have one because of the variations that you're observing. But is that all done? I would say no, because there's few more criteria that you have to add in order to pick up your things, right? So there is what is the energy dollars that you would pay, and what is your per ops IOPS value that you would pay at what levels, right? So these are also extra criteria that now gets added in order for you to pick up whether you wanted to choose between system one or system two. Now, what I want to drive this thing is, in order to pick up which storage system that you need is not a single dimensional variable that you would use to determine which one is that, but there is a series of a series of metrics that you need to consider, and you need to pick up based on your workloads, based on these metric, which band is appropriate for you, and choose a system that falls within this band. So it turns out to be a multi-dimensional optimization problem and is not a straightforward problem of saying that, oh, I did find an IOPS better, so can I pick it up for it? Well, fine, maybe not. You need to still look at other metrics and multitude of these metrics to see whether it fits into your thing, into your requirements. More importantly, you need to understand what your application requires, and that turns out to a question: how do I understand what is the application behavior? Well, you don't understand it just by looking at the application. You need to at least have a couple of runs, a couple of things on, specific settings, understand what it takes to do that, and then probably you may have to come back and work out this model and see where your system is right for you to pick it up in that thing. Okay, so it is an iterative process, and it is not something which you can readily pick up and say, yeah, this suits mine and I'm going to go with that, right? If it is that clear, I think, well, fine, you could pick it up, but it often turns out to be an iterative process to pick up this. Okay. So with that, I think I will stop the presentation and leave it for more questions if there's anything. Otherwise, we can call it for the day.
Yeah, there is actually one question which got missed in the chat box from Radha. It says, what are some recommendation for storage of data for analytics?
So I think the last one that you had looked at, the 5 or 6 things, I think we need to do that exercise. First of all, we need to understand what is the kind of data that you have. And see, there are two kinds of things, right? One is the data, the boxes that we are looking at, storage boxes, and second is the kind of databases that you are looking at, right? So that's a different debate altogether, which database would suit your requirements, and what is the underlying data storage that is used to provision these databases is a second thing altogether. So there is quite a bit of different criteria that you would apply for each of these things, because on the application layer, you will think about whether your data is distributed or whether you are basically, it's an RDBMS or whether it's a graph database. So you will apply a different set of criteria. On the underlying storage, you would only apply these metrics on whether your throughputs are fine or not, and then you would actually decide it. So you first have to understand the workload better and then do it. And how would you understand the better? Maybe you can do just a pen and paper saying that, okay, this is the kind of data I'm seeing right now. If I have to take this on this kind of an IOPS, how much time would I finish this thing? Where is the bottleneck going to be? So you could do that as a paper and a pen exercise, which might be okay to begin with. And then once you do a couple of iterations just on your uh, regular infrastructure components, you could try it, and then you could always adjust your infrastructure components based on what you would do, right? So that's the thing. So if there is a straightforward answer to say what suits AI, I think that's a, $1 million question is what I would say.
Yes, one last question. Are there any best practices for data tiering or data lifecycle management when dealing with AI generated data to optimize storage cost?
Yes, so inherently, if you look at it, there is quite a lot of approaches people take in order to do this tiering. When they wanted to move the data, how stale is the data, whether it makes relevance, whether the stale data is required for the training or not. And it also depends on, what kind of, say, like, say, for instance, if these kind of newer generation generative AI applications, you still need the corpus of data to train those kind of things. So there's nothing called stale over there. But if you look at time series data, if you wanted to look at, say, 10-year-old data, is the last 10th-year-old data, is it relevant or not for your model? So that's the question. And depending on that, people take different approaches to do the tiering itself, right? So tiering has lot of approaches, lot of criteria for tiering, and also cost of how much it is, whether there is insight in that or not. So there's many papers in that, many research work in that thing. There's a whole body of storage metrics in that thing. So I would suggest that probably you can drop me a mail and I can give you all the context regarding how people tier data in the storage boxes.
Sure, sure. I think those were the questions. And participants, if there are any other questions, the last one will be taken, please. Okay, there seems to be no questions. Thank you, Ms. Kalapriya. That was indeed a wonderful session. Ms. Kalapriya, a true visionary and a trailblazer in the realms of technology and academia. We are deeply honored to have her grace our event today by sharing such a valuable topic. We would like to thank Supriya Kamtenia, an expert technologist at HPE, for having these talks planned at the IEEE Forum. We would also like to thank the IEEE Bangalore Section Chair 2023, Dr. Aloknath D., IEEE Bangalore Section Chair 2022, Dr. Deepa Shanoy, IEEE Women in Engineering Chair, Dr. Vijay Lakshmi, and IEEE Site Bangalore Chair, Ms. Anandi Giridharan, IEEE Women in Engineering Chair Elect 2024, Ashwini Holla, for having this session arranged. Special thanks to Mr. Chengappa for helping the team on the IEEE tools to execute the session as expected. A very special thanks to student volunteer Ananya for her contribution in designing the posters for the session. Now I request the IEEE leaders to share some thoughts if they would like to.
Hello, Ashwini here, Ashwini Holla. So I must say I enjoyed the session very well in the fact that this was an eye opener. I'm a novice in this field. I mean, not even a novice, totally ignorant. So this was, something that went on at a very unhurried pace, and even I could, identify. And get to know some nuances here. So I'm sure, most of the people who were here from the start did continue to be, and I could see that it was very interactive. So I must, a special thanks to Supriya for arranging such a wonderful talk, and hope to see more such talks in the future, and hope to see more such interactive audiences as well. Thank you so much, ma'am, for your wonderful
Thank
talk
you
and
so
address.
much. I think it was a Friday evening, and I'm glad that people could stay and listen to this.
Yes, it was very interesting. Thank you.
Yeah.
Thank you, ma'am. That was indeed an amazing session. Definitely a lot was learned for, and I hope the participants have something to take away from the session. And thank you everyone who have put an effort to arrange this meet. Thank you very much. Now I request all the participants to be on camera if possible. We'll take a nice picture. Thank you, everyone. Thank you so much for attending the session today. Thank you, ma'am, again for guiding us through the webinar. It was indeed an amazing session again. Thank you very much.
Thanks, everyone. If you have any questions, you can feel free to drop me an email. Thanks for attending too. Yeah.
Thanks, Kalapriya. Thank you so much.
Bye. Bye, everyone.
Good day.
Thank you.